Ah, damn it. Hi, Rebecca. Don't have my ears on yet, and I just spilled some water. I'll be right there. Wonderful. Ears are going in. How you doing?
I'm doing good. How about you?
Peachy Keen, wonderful. You had no trouble getting the invitation?
Nope.
Because for some reason or other, my class this morning did not get it.
Yeah, I saw that email. I'm not sure. I have class then, so I can't really attend the 9 o'clock meeting.
Yeah, I don't know what happened. I sent it out. 2 people got there. How they got the message and nobody else did, I have no idea. Do you have, Rebecca, do you have lab with me tonight?
No, I don't.
Okay. Hi, Casey.
Sadly.
Hello.
Did I answer your question?
My question?
You had a question. Okay.
I don't think I had one. I don't know.
Again, same thing. You have to understand, I get tons of emails, and as a consequence, it's kind of like I remember people's names, but I forget what they have. So
That's okay. I don't think I had a question though, so.
All right, good. That's fine. That's even better, Casey. Gabe.
Hello.
Did you want to be in the meeting this morning?
Yes, but I didn't get the email or link.
Not even right now, because I did send 2 emails out. I sent, generally speaking, I send one at the time of time or about that the meeting's going to start. And
Yeah,
then if I don't get a whole lot of people in, like today, I sent a second one out at 9:37. The first one went out.
No, yeah, I didn't get any of them.
I do not know what to tell you, Gabe.
Oh, that was fine. I can just join this one.
Yeah, the only thing is you're not going to have in this session, I've already gone through dimensional analysis and matter. Okay.
Yeah, that's okay. That's okay.
It's basically, it's a review of everything we've been doing.
Yeah.
So I apologize. I don't know what happened.
Yeah, no, it's okay. I mean, I was waiting and like refreshing. It must have been some glitch on like the computer or something.
If that happens.
I think I know what happened.
What's that?
I might know. I have you for lab, and I think you might have sent the lecture link through the lab course, because I checked to go on to this lecture right now, and then I saw one from lab from this morning.
No. There is one for lab, Casey.
Oh, okay.
There is one for lab tonight as well. So
yeah, but I think in the lab email, I think it said that was for the morning, which is the time that you do the lecture, because it said 9:30 a.m. for the lab.
There's another one, Casey. Let me get in here, and I got to get into emails. Okay. At least I got 4 people. Now I was lonely this morning. I only had 3. All right. Okay. Casey, this is the one I just sent. Okay.
Yeah.
This is the one I just sent. And you notice the time?
Yeah, I know, but I think I saw one from this morning that you sent through.
That's entirely possible. I may have done that. I may have been in the wrong class. And if that's the case, then it really was my fault. Okay. Nope. Nope, that's not it. You're right. You're set. You're perfectly right. So that was my fault completely. I just have to be more careful. I'm sorry. Sorry, Gabe.
No, no, you're fine.
But at least it's explained. Okay, so.
Professor, I have a quick question.
Uh-huh.
So for the scavenger hunt that you want us to do last week,
Yeah.
I did them like in 3 separate days, and then I noticed that you wanted it under one response.
Don't worry, I'll
So-
figure it out, Gabe.
Okay, I was gonna say, do you want me to go back and do it under one
No,
response?
no. Please. I'll figure it out. Don't confuse things more than I'm already confused, okay?
Okay. And then for the student forum, we didn't have to reply on that. We didn't have to
No.
comment last week. Just
No,
this
we
week.
did. Gabe, what's going to happen is the student forum's going to stay open, and that's
Right.
for you guys to use. Okay?
Okay.
What I'm going to do is I'm going to populate 3 homework assignments every week. And that's only
Okay.
to prime the pump. If you have nothing that you want to comment about, you can solve the homework assignment. Okay?
All right. All right. And then it's like 3 comments per week.
Yes.
Right.
Starting from Sunday through the Sunday after that.
All right. Perfect.
Okay?
Perfect.
So
Perfect. Okay.
all you had to do today was to respond to the questions I gave for the scavenger hunt.
Okay. Perfect.
Okay, let's see. I got so many people. How many people I have in here now? Ooh, 6 people. Everybody, how's the class going so far, guys?
Good.
It's pretty
You're-
good.
You're understanding things?
Yes.
You're understanding things? Everything's okay? I'm sorry about the quiz. I basically either I corrected myself and didn't save it, or I forgot to multiply or divide by 2. And that's probably what most of you guys did if you got the wrong answer. The pizzas were $7.99 for 2 of them, like Domino's, which is where I got the idea basically.
I like your little comments about the anchovies.
Yeah. God, I can't stand anchovies, and my wife loves them. Not on pizzas, thank God. She just eats the things she makes this kind of pasty thing. I just try and stay out of the kitchen when she's there with them.
Like for Caesar salad?
Yeah. Yeah, she, as a matter of fact, that's what she did. She's down in South Florida right now with my granddaughter. So she had to carry supplies down with her. It's amazing. I'm not only supporting a family of her and me, I'm also supporting 5 people from South Florida. Anyway, things going okay? Other than that, semester, everything going okay?
So
Anybody
far, so
have some-
good.
Anybody have any face-to-face classes?
No.
Nope.
I do. It was fun getting back together with people. Had my first one on Friday. My lab's down to 12 people, which is also great because I only have 12 things to grade them. Okay, we got about another minute to go. Got 8 people in here. Woohoo. That means 10 out of the 40 people I have in this class are attending these meetings. I'm going to be interested in what happens in the first test, guys. I'd almost like to see how you guys do versus them. I may not like the answers. All right. We got through, as I recall, we got through dimensional analysis of matter and density last week. Is that correct?
Yep.
Yes.
All right, so I have to go through temperature and I have to go through Nope, that's not what I want. Yeah, maybe it is. Temperature, then we're going to get onto the history, and I'm sure you're going to be riveted by that, guys. The thing about it is, I give more information than is in the book. So your being here will be a benefit to you. And I'm trying to find the right. Okay. All right, so temperature. Guys, this is thrilling stuff. Go back to the top. Slideshow. Current slide. Everybody can see temperature up there, correct?
Yep.
Yes.
Yes.
Okay, guys, we have 3 scales. Fahrenheit, I will try not to use the F word. Celsius, I will interchangeably use Celsius with centigrade. And I'm sorry, I'm waiting for some people to get in here. Okay, so I will use centigrade and Celsius interchangeably. And the last one is Kelvin. I will get organized here. All right, Fahrenheit, Celsius, and Kelvin. Kelvin's basically the best one because it relates everything to absolute zero. Absolute zero is when the molecules stop moving at all. So anybody know what the boiling point of water is? Celsius. We'll go with the easy one first. Celsius. Boiling point of water.
100.
100 degrees.
Freezing point Celsius.
0.
Freezing point Fahrenheit.
32.
Okay, now the hard one. Boiling point Fahrenheit.
273.
Nope. 273 is the conversion from Kelvin, Celsius to Kelvin.
223.
Close. It's actually 212.
Oh.
So if we were going to compare these things, one to another, if we're going to compare them, okay, we don't start off at the same place, do we? We start at 0 for Celsius. For Fahrenheit, we start at 32. If we're going to deal with freezing point and boiling point, right? Does that make sense to you? I need to hear.
Yes.
I need to hear the rattle of your heads, guys.
Yes.
Okay, thank you.
Yes. Professor?
Now, if the boiling point in the Fahrenheit scale is 212, the difference between 212 and 32 is 180 degrees. The difference in Celsius is only 100. So the rate per degree is going to be, the degrees for Celsius are larger than the degrees Fahrenheit. Does that make sense to you?
I think we already went over this.
We went over this?
Yes. Yes, we did. We already went over
Then
this.
stop boring me. Sorry, I thought when I said temperature, I naturally assumed that you guys would yell at me earlier if we went over this. And I was on a roll too, guys. Okay,
I did
so
have a-
now, question?
Yes, I had a question about the quiz, but I can wait till after if you prefer.
Go for it.
There was the true or false about whether the
Is this
metals.
Blake?
Say
Is
it
this
again.
Blake?
No, this is Nathan.
Negative.
Nathan. Okay, Nathan. The right answer should have been true. I went back and regraded it.
Okay.
It worked out. When you did the calculation, if you did the calculation and didn't divide by 2 because it was $7.99 cost per 2 pizzas.
No, I was talking about the metal question. It asked if the metals sat on the left side.
When you did that density, when you turned pounds into grams, and you turned.
No. It was just about the periodic table. It just asked if your if the metals sat on the left side of the screen, or the left side of the table, sorry. Didn't know if it was like, it just said, it was kind of vague, the question was. It said, does mostly the metals sit on the left side? I went by the assumption that it was including the transition metals. And so I put false, thinking that the right answer was that they would be in the middle rather than the left.
Okay, but it doesn't go from the middle all the way to the left.
Yes. Okay.
Okay?
Yeah.
Okay, where am I at? Are we still seeing this? Are we seeing this screen?
Yes.
We're seeing chapter 2. Okay, who was that? Nathan that asked the question?
Yes.
Okay, are you satisfied with my answer, Nathan?
Sure.
Sure.
Yes, I am.
I will look at it and see if I think that the question was vague, okay?
Okay.
Now, the things we're going to do in this, we're going to go through the history of atomic theory and structure. We're going to deal a little bit with conservation of mass and energy, more conservation of mass than energy. Then we're going to get into the structure of the atom. We're going to talk about isotopes and the average mass calculation. We're going to give a basic tour of the periodic table. Talk about valence electrons, ionic and covalent bonds. Then we're going to get into nomenclature. That basically, if you look at this, this is basically encompassing three of our next lectures. Now, again, these are the topics I consider important. So these are the topics which are outlined in the online outline, okay? Okay?
Okay.
Thank you. So, atoms compose matter. The property of atoms determine the properties of the matter, and the atom is the smallest identifiable unit. We went over this last week, right?
Yes.
Yes.
Thank you. Who's going to be my yes man?
Not it.
Basically,
Jeez.
there are about 92 natural elements. You go up through uranium. Those are found in nature. Everything above 92 is a man-made element, which are basically only useful in getting your Nobel Prize. If you don't want to get a Nobel Prize, then don't worry about it because it's not useful. Now, charges may be positive or negative. You know that from a magnet, right?
Yes.
Okay. Opposite charges attract, while like charges repel, correct? If we were going to think about the force behind a positive and a negative being attracted to each other, or the negative and the negative being repelled by each other. If we're going to look at that force comes down to an equation which is called Coulomb's law, in which the force is related to some constant K times the charge on the first particle multiplied by the charge on the second divided by the radius between them. Now, if I have a positive and a negative, that's attraction, correct? That is something that's, push them together, that's more than likely going to happen, correct?
Yes.
So if I get a positive times a negative, what is the sign of my force?
Negative.
All right. If I have a positive times a positive or a negative times a negative, what is the sign of my force?
Positive.
Positive.
So if I have a positive and a negative, that's going to be a force that has an exothermic note to it. If I have a positive and a positive, that's endothermic because I got to force it into happening. Does that kind of make sense to you?
Yes.
Now, we're going to get back into the history of the atom and how everything came about. The first guy that proposed something was a old Greek guy by the name of Empedocles. And basically, he's the one that came up with the theory that matter was composed of 4 basic elements: fire, earth, air, and water. Democritus said, "You're full of crap." Democritus says this is ridiculous. Matter is composed of small individual particles, than which he called atomos. And basically what he said was that atomos could be combined in different ways to give rise to the amount of different substances that are on the earth. Finally settled. What happens? You get 2 big guys that are fighting it out. You get a referee. And the referee was the head honcho of the Greek scholars, Aristotle. And basically, Aristotle settled the matter. Boom, boom. Thank you. Thank you. Thank you, Gimme. Thank you for allowing me a bad joke. What Aristotle did was he supported Empedocles' theory. So basically, the atomic theory was not accepted until 2,000 years later. Now, a guy by the name of Robert Boyle. Robert Boyle was a fantastic thief, guys. He stole the law that was named after him. So, but he did come up with this thing. And basically he said that an element is a substance that cannot be broken down into simpler substances. I kind of added that last little thing over there because by a chemical reaction, because we know that uranium breaks down into other elements by radioactivity. Different concept. You'll get into radioactivity in the very last part of Chem 2. So what Robert Boyle says is that elements can't be broken down into simpler substances. Joseph PROUST, discoverer of oxygen. He came up with the law of definite proportions that I've already talked to you about. Now, what he did was he came up with the idea that each compound has exactly the same proportion of element by mass. We now know that that can be correlated to a given compound has the same proportion of atoms to other atoms in the molecule. And what I mean by that is if we have water, we have 2 atoms of hydrogen, 1 atom of oxygen. What PROUST would interpret that to mean is we have 2 grams of hydrogen for every 16 grams of oxygen. That makes sense to you all?
Yes.
Yes.
Did he also coin constant composition, or was that coined later on?
I think Dalton did that.
Okay.
That would be something. Thank you for asking the question. I'm not entirely certain. I believe it was Dalton, but I could be wrong. It could be, yeah, I could be wrong. Now, the interesting thing, guys, I don't know if you noticed this or not, if you ever knew this or not, all the scientists back here, all the scientists that were doing this way back in the 16th, 17th, 18th centuries, science was a hobby to them. There were no occupation scientists. They all did something else. Dalton was a school teacher. If you think about Franklin, Benjamin Franklin, by the way, this is how I know about this. Benjamin Franklin, I was reading a book, and how did he earn his money? He was a printer. He earned his money being a printer, but his hobby was studying electricity. All these guys did something like that. So basically, Dalton came up with the premise of the atomic theory. And his premise had 5 different parts. He said, first of all matter is made of atoms. Second thing, all atoms of a given element have the same mass and properties. Compounds are formed by the combination of 2 or more atoms. We're not very far from Democritus, or whatever the silly guy's name was. If you have a chemical reaction that involves a rearrangement of the atoms, and The last thing is important because at this time, people were still trying to convert lead into gold. Dalton basically came out and said, you cannot arbitrarily convert one element into another. A little further on down, later in the 19th century, we came across a guy by the name of Dmitri Mendeleev. And what Mendeleev is a friggin' genius. What he started to do was he started to group all the elements in terms of their properties. And basically what he found is that certain elements had the same properties. For example, every potassium bonded with one potassium bonded with one chlorine. He also found out one sodium bonded with one chlorine. So he kind of like put this in the back of his mind and said, okay, we're going to lump these two together. Then he said, okay, calcium bonds with two chlorines. I'm going to put calcium in a different pile because it reacted differently than sodium and potassium. Found out that magnesium also bonded with two chlorines. So he put that in the pile with calcium. And basically what he did was he compiled a table that looked pretty much like this. And he came up with certain blanks in his table. For example, germanium was not an element that was discovered when Mendeleev created his chart. He predicted it, but it wasn't there. It waited a couple of years until germanium is a phosphorescent element, which means it glows in the dark. There was a mine in Sweden which was mining these rare ores, these phosphorescent ores, and they later determined that germanium was one of them. So he predicted the periodicity, something like that. Basically, he said that elements were periodic in their properties. He created families, and he also predicted elements based upon the holes in his table. Guys, I don't know if you realize what an amazing time the turn of the 20th century was. There was so much knowledge that was created during that time that it dwarfs everything else that's been created. Again, personal opinion. Great time. If I ever had to be reincarnated into another time, I'd want to be around the time of Teddy Roosevelt's presidency. So we started off with J.J. Thomson. Now, what Thomson was doing was he had what was known as a Crookes tube. What a Crookes tube does is it generates streams of electrons so that these electrons would go from the source and they would hit a metal plate. Now what Thomson did was he put a magnet on top of it with the positive side, on the bottom of it with the negative side. And he watched the stream of electrons start to tilt towards the positive side. So naturally he deduced that this particle, which is part of the atoms, has a negative charge. He correlated that with the fact that when you touch matter, anytime you touch something, you don't get shocked. So this negative charge must be balanced by a positive charge. And what he created was something called a pump-splitting model. Did this. Okay, has anybody ever eaten a Jell-O fruit salad?
No.
Anybody have any idea of what I'm talking? Anybody seen any movies from the 50s in which they had this Jell-O fruit salad?
Yes.
Thank you. Thank you. I have now been reaffirmed to be back on life in the planet Earth. That I am not so antiquated that somebody at least doesn't know what a fruit salad is. Basically, how you make a fruit salad. you start the Jello, and you start to put it in the refrigerator so that it starts to get that jelly-like portion. Then what you do is you add little pieces of fruit, like apple slices, grapes, things of that nature, so that you get all of these things suspended in amongst the Jello. Okay? Let me ask this question. Does anybody know what a plum pudding is?
Yes.
Same person answered.
It's like a blueberry muffin, right?
I'm sorry?
It's like a blueberry muffin.
All right, we'll go with that.
You
Yeah.
boil it.
Well, it looks like a blueberry muffin. You have something that's kind of holding things, but you got the blueberry particles in there. And basically what he said was the muffin part is kind of like the positive part, and the little particles in there are the electrons. Okay? Not a very good theory, but it's the one he had at the time. Guy by the name of Robert Millikan, what he did was he determined what the charge of an electron was. And this was important because he was able to determine from the charge, we were able to determine what the mass of that electron was. So he had an experiment called the oil drop experiment. And he had a mister. He didn't have a missus, he just had a mister. He was funny that way. He had a he had a thing that would allow him to spray oil droplets into a chamber. Now, the oil droplets are going to fall because they have gravity, right? Now, he had one little slit in there so that he was able to get one of these oil particles to go through that slit. And what he had was voltage created. So the voltage created a negative charge, and that negative charge, when attracted to the positive end of the electrical field, made it go faster. So basically, he compared the acceleration of the oil drops without the charge to the ones with the charge. And that's how he came up with his mass to charge ratio. Now think about this. He's watching oil droplets fall through a vacuum tube. This is almost like biologists counting the plankton in a certain area of a slide. I couldn't imagine. What I would do is I'd slit my wrist before I got through the first part of the research. In any case, he lasted himself, and he was able to come up with this theory. Now, Ernest Rutherford, a guy from New Zealand, he was a student of Thomson. And so basically what he wanted to do was he wanted to prove that Thomson's theory was correct. So what he decided to do was he decided to set up his famous gold foil experiment. And the whole idea behind this experiment is he had a source of alpha particles. An alpha particle is nothing more than a helium atom. These alpha particles were accelerated through and at a thin gold film. And basically what Rutherford was expecting, what Rutherford was expecting was he was expecting most of these to pass through. He was expecting none of them to pass through because you had a solid atom there. But what he found in reality is that some of the particles, some of those alpha particles bounced back. Others bounced and were reflected. But the great majority of the alpha particles went through. What he was able to say from this is that the atom is composed mostly of space. He was succeeded by a man by the name of Max Planck. Now, there was a great catastrophe in the field of electromagnetic radiation. What happens is as the wavelengths of light get, as something gets heated, the wavelengths of light are supposed to get smaller and smaller and smaller. Well, what happens is this happens to a certain degree, and then they start to get larger again. Electromagnetic wave theory could not predict this. So Max Planck started to come up with the idea, well, what would predict this is if the energy emitted was not wavelength, but energy was emitted in small little packets that he called quanta. Okay, think of it this way. Electromagnetic radiation is like walking up a ramp. You have a nice steady walk all the way up. What Max Planck was proposing was walking up steps. You have to have a certain amount of energy to get you to the first step, more energy to the second, and so on and so forth. Well, what this led to a guy by the name of Niels Bohr, who combined both Planck and Rutherford's theory. And what Bohr said was that electrons travel in specific energy levels that he called orbitals. Mainly, it looked like a solar system. And the energy between these orbitals is related to the quanta, or the energy between the two orbitals. The higher the orbital level, the higher the energy. All right, backtracking just a bit. That's all the further we're going to go on the atom itself. Right now, we know it has a hard center and it has electrons floating in orbitals out of there. Couple more people we need to be aware of. First of all is Antoine Lavoisier. Do you remember I said that these guys used to do science as a hobby? Lavoisier was actually a financier for Louis XVI. Anybody remember what happened to Louis XVI?
Nope.
Nope.
He was murdered.
You might say that. Louis was marched right up to the guillotine, and he soon lost his head over the experience.
That was a good one.
Lavoisier, because he was a member of the noble class, suffered the same fate. But before that, he came up with a theory that he called the law of conservation of mass. And basically what it said was, if you do a chemical or a physical change, you can't gain or lose any mass. The mass just gets moved around. What two elements make up water, guys?
Hydrogen and
Oxygen.
oxygen.
Okay. Do you know how hydrogen and oxygen appear in nature? Is it just an H and an O?
No,
What is it?
they're diatomic.
Diatomic, meaning for those of you that don't know it, a hydrogen exists as H2, one hydrogen linked to another. And oxygen exists as O2, one oxygen linked to it. So basically, if I have an equation for water, I have H2 and O2 reacting to make H2O. What's wrong with this picture?
You lose oxygen molecule.
This equation is saying that I've destroyed an oxygen atom. And that is not what, that doesn't adhere to the conservation of mass. So what we have to do when we're dealing with the conservation of mass, we have to react two hydrogen molecules with one oxygen molecule, and out of that we get two waters. This is why balancing chemical equations is so important. Hold on a second, guys. Sorry, my throat was getting dry. All right. Later on, they discovered that not only is mass conserved, but energy is also conserved. Basically the same, a corollary law. In chemical and physical changes, energy is never gained or lost. It's just transformed from one form to another. Basically, the forms are kinetic, involving movement or involving work being done, and potential, which is basically the energy of position or of composition. Now, later on, we found out through Einstein's theory of relativity that this isn't exactly true. Basically, we can have energy being transferred in the mass, and we can have, more importantly for Nagasaki and Hiroshima, mass can be converted into energy. Because basically, what happens in a radioactive uranium bomb? The uranium gets hit by a series of neutrons, and the uranium breaks down into two smaller compounds. The trouble is the addition of the weight of the two smaller compounds doesn't add up to uranium's weight. That is called the mass defect. And the amount of mass lost gets changed through this equation into energy. So that's basically how a hydrogen bomb works. Basic definition of energy. It's just basically the capacity to do work. And as I said, can be divided into kinetic and potential. Kinetic is, potential energy is the energy associated with position or composition. You have that little 10-year-old boy that decides just on a lark, he's going to get into a barrel in Niagara River and he's going to float down and go over the falls. The position he's at Goats Island in Niagara Falls is the position of potential energy. He's at a higher location. Once he falls over the falls and is moving, that becomes kinetic energy. Now you notice I also said composition. When we're dealing with potential energy in chemical reactions, we're dealing with chemical bonds. Chemical bonds have energy. It's the energy that holds a molecule together. Now, what happens is when you're undergoing a chemical reaction, bonds get broken. The bonds get broken by putting in more energy to break the bonds. You have to put energy in to break the bonds. Now you have these pieces floating around. But the pieces that are floating around eventually hook in together, and when they hook in together, they make new chemical bonds. Now, if the potential energy of the new chemical bonds is less than the potential energy of the original combination, you have an exothermic reaction. Heat gets transmitted. If the exact opposite is true, if the energy of the new compounds is greater than the energy before you started, that is endothermic because the compounds had to absorb energy. So when we're talking chemical, potential energy in chemistry is dealing with the chemical bonds. Again, kinetic
I have
energy,
a question.
Go for it.
So which of those would be involved in the nuclear bomb? Would it be endothermic or exo?
They're very much exothermic. I think I figured it out once that in my Chem 2 lecture, I think I compared blowing up half a pound, a mole's worth of uranium, blowing that up versus a mole's worth of reacting like hydrochloric acid with sodium hydroxide. That was on an order of like e to the 15th more for the radioactive bomb. Okay, we good there?
Yeah, thank you.
All right, kinetic energy is the energy associated with motion or the energy associated with doing work. We are going to get back into this during the chapter on thermodynamics. Now, as I was explaining earlier, if you have less potential energy in the reactants than you started with, in other words, if the energy of the chemical bonds is less for the reactant than the energy for the reactants, then that energy has to go somewhere. That energy is generally released in the form of light, heat, electricity. In some fashion, that energy is released. So if energy is released during a chemical reaction, that is called exothermic. If it is absorbed, that is called endothermic. And in terms of our chemical model, if we have an endothermic reaction, this means the bonds of the products have more energy than the bonds of the reactants. Exothermic would be the exact opposite. Are we good? Any questions?
I'm kind of just curious of an example of an endothermic reaction.
Okay, have you ever broken a bone or had a severe sprain?
Yes.
Okay, did you have a cold pack applied to that?
Yeah.
Okay, what they did with the cold pack is it's not a reaction that's happening, but what a cold pack is it has a packet of the powder in it, and it has a packet of water in it. By crashing those two together, by smacking them together, you break the seal, and the powder gets dissolved in the water.
Does that mean that usually I'm sorry, does that usually mean that when an endothermic reaction happens, that it usually creates kind of a cold feeling?
Yes, because what's happening is the energy from the environment, anything that's touching that chemical reaction, the chemical reaction is absorbing things from the outside. So if it's absorbing energy from the outside, that energy is in the form of heat. So the outside actually gets colder because the energy has been delivered into the thing that the endothermic reaction.
Perfect, thank you.
Now, signs. Exothermic reactions have a negative energy. Endothermic reactions have a positive energy, because when you have an exothermic reaction, it released energy, so whatever is less has less energy than what you started. And endothermic has absorbed that energy, so it has more energy than what you started with. It's positive. Any more questions, guys, before I go on to the parts of the atom? Let's go for it. Okay, we have the masses. If you had a scale tiny enough, you would be able to come up with the mass of a proton, mass of a neutron, and the mass of an electron. Are these numbers really, 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 really small?
Yes.
Is it realistic to be able to weigh something this small?
No.
So what we did was we had to choose a standard. We actually started with oxygen. I think it was PROUST that might have started it, but it doesn't matter. We started with oxygen. The reason we don't use oxygen is very, very, very reactive. So we wanted something that had a little more stability to it. So the thing that's most abundant and the thing that's fairly stable is carbon. So we chose carbon 12. that is a carbon atom that has 6 protons and 6 neutrons. So basically, if we multiply 6 times the mass of a proton and 6 times the mass of a neutron, we have the weight of a carbon atom. So we've decided to come up with a unit. The unit is called the atomic mass unit. 1 AMU is equal to, you multiply these things out, right? 6 times this plus 6 times this, the number of particles is 12. So you get this 6 times this plus 6 times this gives you 2 times 10 to the minus 23. You divide that by 12, you end up with 1.67 times 10 to the minus 24. So 1 AMU is equal to this number. So we don't want to mess with some numbers so small. So basically we're saying, in effect, the protons and neutrons have a mass unit of 1. Electrons are so tiny that their mass is negligible. Blake, you there, Blake?
Yes.
Okay. Blake, have you ever walked across 66th Street from the school?
I have not.
Now you are. Okay? You are just about to step across off of the sidewalk, and you're trying to cross 66th Street at 5th Avenue.
Okay.
Unbeknownst to you, barreling down 66th Street in a south manner, there is a truck which weighs 2,000 pounds.
Oh,
In that
geez.
truck, it's driven by a hippopotamus, which also coincidentally weighs 2,000 pounds. And this hippopotamus has in his passenger seat his 2 friends, mice, which weigh about 1 pound apiece. Now, Blake, when that truck slams into you, are you going to care about the weight of the mice?
Probably not.
Not
So that's
in the
why we
least.
don't. That's why we don't equate for that in the mass. It's just 12 instead of whatever.
Because of the fact that
remainders.
they are insignificant.
Gotcha.
Let's look at the, let me go back to this thing. Add these up. Add these numbers up. Remember, if I want to equate this with these numbers, this would be 0.00091 times 10 to the minus 24th. Doing
So if
our significant figure rules, it is insignificant. That is why we don't use the electron mass when we're calculating atomic weights.
Gotcha. Okay, cool. That clarifies it. I'll always remember getting hit by a bus driven by a hippopotamus.
There we go. Glad to put that image in your mind. Okay, so when we're dealing with this, remember we've equated an AMU with 1.67 times 10 to the minus 24th. So to get the mass number, basically each one of those 1.67 times 10 to the minus 24th is the weight of 1 proton or 1 neutron, right? So to get the mass number of an element, all you're going to have to do is add the number of protons and neutrons together. Now, what makes an element unique? The thing that makes an element unique from every other element is the number of protons it has. Number of protons define the element. You can't lose or gain protons and still be that element. The number of protons is called the atomic number Z. Now, if atoms in their ground state are charge neutral, and if the charge of a proton is positive and the charge of an electron is, don't know where I was going here. The charge of an electron is negative. What does that say about the number of protons and the number of electrons in a charge neutral atom?
They're the same.
They're the same. They're absolutely the same. So number of protons equals numbers of electrons. But an atom can gain or lose electrons. When it gains or loses electrons, what happens to the atom?
Would it become an isotope?
Nope.
It would be
Okay.
positively or negatively charged.
It becomes an ion. It becomes a charged entity. If an atom loses electrons, what charge does it have?
Positive.
Positive.
It has less electrons than it did normally, so therefore there are more protons than electrons. It has a positive charge. If it gains electrons, what charge does it have?
Negative.
It has more electrons than when it started, so there are more electrons and protons, negative charge. Now, neutrons can have differing numbers. An atom can have a differing number of neutrons and still be that same atom and still have the same properties. Number of neutrons is n. Why, oh why, do we bother with this? A proton defines the atom, defines which atom we're talking about. An electron, basically, because it can gain or lose itself, it defines the properties. What's the purpose of neutrons?
They make isotopes.
Nope.
Is it balancing out the charge?
Nope. Neutrons are neutral.
Balancing out the mass.
That's part of what it does. But why? Why do we have neutrons? Think about it. What's on the charge? What's the charge of a proton?
Positive.
Positive one.
So if we just have protons in the nucleus, what would keep the nucleus together? You would have all these positive charges basically repelling the other positive charges. That would be too great for the nucleus to overcome. On the other hand, if you separate the positive charges with neutrons, and does one body have an attraction to another body? And I'm not talking about at Park and Rec on a Friday evening. Is there an attraction between the moon and the earth?
Yes.
How do you know that?
Gravity.
Not gravity.
One another.
Why do you know that the moon and the earth have attraction?
Because they orbit one
twice a day.
I mean,
The tides.
Tides.
Oh, yeah.
We have tides because there is an attraction between the moon and the earth. So that proves that there's an attraction between one body and another body. So what happens when you get neutrons and protons? It's that attraction of one body to the other that overcomes the amount of positive charge in the nucleus. So that's why we have neutrons. The neutrons are there to keep the nucleus together. Protons identify the element, electrons give the element its properties, and neutrons keep the nucleus together. So if I give you an atom of sodium, and I tell you there's no charge on this sodium, and I tell you there are 11 protons in sodium, how many electrons must there be?
11.
Has to equal out because I said it has no charge. Now again, I said this earlier, the number of protons is known as the atomic number. It is designated with the letter Z. It's the smaller. If you're looking at a box in a periodic table, it's generally the smaller number. The mass number tells us how many particles are in the nucleus. So if I know the number of the mass of the atom, and I know how many protons there are, can you tell me how many neutrons there are?
6.
How do you do it?
10 minus 6.
Remember, the mass number A is equal to the atomic number Z, which is the same thing as the protons, plus the number of neutrons. Okay? So if I know the mass number and I know the number of protons, if I know what element it is, all I have to do is take A minus Z. That will give me my neutrons. If I know the protons plus the neutrons, if I know both those numbers, I can tell you the atomic, the mass number. If I know the mass number in neutrons, I can also tell you the protons. Again, am I saying anything that is silly at this point?
No.
Correspondingly, if I know the charge of the ion, I know that the charge is equal to the number of protons, the Z, minus the number of electrons. So we need to start filling this out. And it may take me a while to come up with a name, but I will come up with a name. Rebecca, I know you're there. I have potassium. Does the potassium have a charge, Rebecca?
No.
Does not have a charge. What does that tell you about the number of protons and the number of electrons?
They're the same.
So how many electrons do I have?
19.
Okay. Min, are you there, Min?
Yeah, I'm here.
Okay. I'm going to give you a hard one. Calcium 2 plus. I have to give you one other number. Okay. I have to give you that the mass number is 40. Okay.
Okay.
All right. I've identified the atom. If I've identified the atom, I have identified the atomic number, which corresponds with protons. Min, do you have a periodic table in front of you?
No.
Okay, guys, next couple of lessons, bring your periodic table. Can anybody tell, Min, what the atomic number for calcium is?
It needs 40.
The mass number is 40.
20.
20.
20. Atomic number for calcium is 20. So, Min, if you know that, how many protons do you have?
20.
Okay. Remember, protons plus neutrons equal the mass number. Mass number is 40. I have 20 protons. How many neutrons do I have?
20.
20. All right. Now I have my number of electrons to figure out. I have an ion here. It's 2 plus. So 2 plus is equal to number of protons minus number of electrons. Okay? So 2 plus is equal to, you told me the number of protons was 20. So 2 plus is equal to 20 minus what number?
Not 18.
18. Did everybody follow my logic there?
Yes.
All right. I have to give you something. Oxygen exists as O2 minus. I didn't need to give you the protons. You could have figured that out just by looking at the atomic number of oxygen. But what I do need to give you is the mass number. Gabe. You there, Gabe?
I'm here.
Okay. Oxygen is a -2. All right. The mass number is 16. You have 8 protons. How many neutrons do you have?
It'd be 8.
It's 8 because protons plus neutrons equal mass number. 16 is equal to 8 plus 8. So I have 8 neutrons. Okay, Gabe, while you're there, the charge is -2.
here.
Remember, charge is equal to protons minus electrons. If the charge is -2 and you have 8 protons, how many electrons do you have?
6.
8 minus 6 is what, Gabe?
Oh, 2.
What kind of a 2?
Positive.
So I told you that oxygen had a -2 charge. How many electrons do you have?
Would it be a negative number?
Nope,
Oh, negative 10.
not -10, just 10. Because
Oh,
the
10.
formula I gave you.
Oh, 8 minus 10. Oh, yeah. 8 minus 10 is -2. Okay.
There we go. Okay. I gotta see who else is. Did I see Jessica out there?
Yeah, I'm here.
Hi, Jessica.
Hi.
Magnesium ion is a +2.
+2.
Hold on 1 second, guys. Bye. Sorry, I'm very, very sorry, guys. It came from Coral Springs, and my wife is down there with the kids. I thought it was an emergency. I apologize to you. Jessica, you still there?
Yeah, I'm still here.
Okay, magnesium has a +2 charge. Do you have a periodic table in front of you, Jessica?
Yeah, I do.
Okay, what is the atomic number for magnesium?
12.
So, atomic number is 12. Well, how many protons do you have?
12.
Guys, by the way, you should be trying to do these along with us. Jessica, if I tell you that the mass number is 24, how many neutrons do you have?
12.
All right. We have 12 protons. The charge is a +2. How many electrons do you have?
10.
Correct. I'm just going to let it go. All right. Gotta love modern technology, guys. Layla, are you out there? I'm hearing crickets, so that would be a no. Jackson, you out there, Jackson?
Yeah.
Fluoride. Fluoride is a -1. It has a mass number of 19. Do you have a periodic table, Jackson? Jackson?
Yes.
Okay. Do you have a periodic table?
Yes, I do.
Okay, so what is the number of protons?
19.
Is that right? What's the atomic number of fluorine?
9.
19.
Not 19.
No, the atomic number is 9.
Atomic number is 9.
Oh, yes.
So if the atomic number is 9, how many protons do you have?
9 protons.
9 protons. All right, I'm telling you that the mass number is 19. How many neutrons do you have?
10.
Okay. if fluoride has a -1 charge and you know that it has 9 protons, how many electrons does it have?
10.
Guys, I'm spending a lot of time on this. So what you have to realize when you're studying something, if the professor spends a lot of time on something, you can be very real sure that that's going to be on the test. And you are going to get it in a box just like this. Do we have a question, guys? Any questions about that?
No.
We good? Okay, I really don't want to get too far ahead of the other class. So basically, what I'm gonna, I'll go through. I'm gonna drop it right now. So marking on here, we got through until isotopes. There's a tricky aspect to determining mass weights of the elements. So I want to go through it while we're fresh so that we get that. So guys, if we can review the things I've really, the types of equations I've gotten through so far. Density, I have done temperature equations, dimensional analysis equations. And we have gone through these equations here in terms of determining how many protons, neutrons, and electrons are there. If I don't have any questions, please feel free to leave at this time. Now is the time that you can ask questions on things like the quizzes or anything. Oh, before I leave you guys, are you getting the news for the assignments that I assign on Sundays? Are you seeing that?
Mm-hmm. Yes.
So hopefully that will help make sure that you at least know what's going to be due that particular week. I think that's the only thing I've added.
Is there a study guide for us?
Yeah. Let's just think about this. Remember, I told you the topics. The topics are your study guide. That includes everything I think is important in the chapter, in chapter 2. Now, are you asking me specifically, is there a practice test? Is that what you're asking?
Yeah, but this is fine.
I do include practice tests, and I get lambasted each time I do it because, ladies and gentlemen, I am a horrible editor. I think you can tell that by the quiz 2, that first question. What happens is I get locked into something, and when I go back to redo it to check my work, I get locked into that same mindset. So what happens is I end up giving wrong answers on my practice tests. I'm sorry, it's a fault of mine. It's something we have to live with. Anybody else have any questions about anything?
I have a question.
Yeah.
So I have a question about the quizzes and the tests.
Yep.
So the quizzes are open note or no?
How am I going to check you? Are you being proctored?
All right. Good response. And then the exams are open note, and then in the future, is the final open note or no?
Yes. Yes. Everything is open book. You have access to everything except other browsers or your phone.
Okay.
It's just too easy to Google answers.
Can't make it that easy.
Well, I could. It'd be easy to grade the things. I do have some morals. Some. Anybody
I
else?
have
Go ahead.
Yeah. About the homework. Is there any other, I guess, scheduled homework other than what is listed as extra homework?
No. Have you gotten your access to My Lab and Mastering?
I don't believe so, but
You have
Get
to.
that.
Who's
Yes,
talking?
Nathan.
Nathan, get that as soon as possible. You've already had one assignment that's overdue.
Oh, okay. All right. I'll get that done today.
You have first homework assignment is due on Thursday.
Okay.
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 Nathan,
Yes.
you can turn in the homeworks late. You're penalized 5% per day down to 70%.
Okay. No problem.
Okay, so get that. That's one priority for you.
Yes. Thank you.
The mastering homework. And you, Nathan, if you're on the home page of the course, you scroll down, the bottom thing to the left is how you access My Lab and Mastering.
Okay.
That's how you purchase the code, and that's how you log into it, okay?
Okay. Thank you.
Anything else, guys? Questions about the quiz?
Yeah, I have 2 questions real fast.
About what?
All right, the first one is about the homework. Is homework 1 the only one that's due by this Thursday? There's nothing else that was due?
The homework in My Lab and Mastering, the Pearson homework, that is the one that is being graded. Okay?
Okay.
Those homework
All right.
questions.
And then
Okay, just let me explain one thing. Those homework questions aren't as good as the extra homework questions. That's why I toned the homework down from 2 hours to 1 hour. I figured that extra time you can look at the other homework and at least attempt some of the assignments there. The extra homework does mimic the tests quite well.
Okay. And then for quiz 3, is that going to be on chapter 3 or is that going
to
be where we stopped today?
Basically, quiz 3 will cover in depth atomic theory, the atomic theory and the history. And it will get into conservation of mass and energy, as well as heavily into atomic structure. Now, you will have lighter questions on the periodic table and valence. The way it works, the harder questions will be on the material I have already lectured on. The easier questions will be the ones on the lecture that is going to be presented the day that the quiz is due. Does that make sense to you?
Yes, that makes sense. Thank you.
Okay. Anything else, guys? Been a pleasure. Go ahead.
I'm so sorry. I got a question on sig figs. I know I'm a little behind. Can I post it in chat?
Yeah, absolutely. That's what Blake. That's what is what chat's for.
All right. Well, actually, no, it's not. It's not loading. But basically, it has to do with sig figs when they're being subtracted or added in parentheses. You're only supposed to go to the decimal place instead of the full significant figure. I don't know. It's
give me a question, Blake.
Can I just email it to you? I feel like visuals would be helpful because these are pretty big numbers.
Okay. Sure.
So if that works,
Blake,
okay, cool. Yes.
Blake, what I want you to do is I want you to go into the discussion forum.
Post it there. Copy that.
Post it there. If you do not get an answer in a reasonable time. Okay, what I'm going to do is I'm going to stop sharing here. You said that you couldn't get into this.
Yeah, it just won't let me copy and paste the snippet I took. I took a screen share, or what do you call that?
Okay.
Print screen.
I'm trying to figure out where I think this is the right one. Okay. So what you're saying is it's not allowing you to cut and paste.
In the Zoom meeting, yes, but not on the forum. I could handle that.
Okay, I'm sharing right now the forum. What I'm talking about is this thing where I say student talk.
Mm-hmm.
Basically, just click onto it and it'll eventually load. And basically hit start a new thread.
Okay, copy that.
And
Will do.
put your question there. If you don't get an answer in a day or two, then post it to me. And go ahead and post it to me anyway, Blake. But that's an example of making a significant response to the forum. Does that make sense to you, Blake?
Yeah, definitely. I'd rather get points for something than So
Okay.
Cool. Thank you.
And I do, Blake, if you're still there, I do look over. Periodically, I look into student talk to make sure that a wrong answer is not being distributed. Does that make sense? And that's really
Okay,
the only
that's
reason
good to
I'm
know.
in there.
Cool.
Anything else from anybody? Okay, guys. Have you been seeing the recordings? Are the recordings being done okay for you?
I have it checked.
I haven't heard anything bad so far, so I'm assuming that everything is going okay, which has been the downfall of me in the past, but assumptions do make asses of you and me. Anyway, guys, if that's it, I will see those of you in the lab at 7:15. 7:15, guys. Okay. Take care.
Thank you.
Thank you.
Bye.
Thank you.
Thank you.
Bye.
Is anybody hanging around to talk to me individually?
I'm gonna go eat before the next lecture.
Good for you. I'm waiting until after it.
There you go.
There we go.
All right, see ya.
Take care.